I think first of all, I would really like to thank you, THPCA, and also Mahanakon University for this opportunity. I think it's an honor and it's a pleasure to be here, to be standing in front of you all. But first thing first, before I actually start talking about the topics that I have prepared, I briefly speak in Thai. So I think we all have this booklet that we got during the registration. The organizer would like to let you know that, oh sorry, I said I would speak Thai. ตรงหน้าสารบัญนะคะก็คือทางผู้จัดแจ้งว่ามีแก้นิดหน่อยนะคะตรงหัวข้อที่23นะคะจาก MOEST นะคะเป็น MEOST นะคะจะมีตรงนี้ที่ขออนุญาตแจ้งไว้ตรงนี้นะคะ and now I will take that ฝากก่อนได้ไหมคะ Okay, so again, thank you for your time. So I'll be speaking or talking about the predicting reliability with engineering simulation. So I think if we're all here, we know that we all might have heard about engineering simulation, and I think we are all interested in how do we perform reliability tests in the most efficient way and also in the most reliable way as well. So I would like to first talk about the usual product development cycle, or like the step. So typically after we have designed our PCB, our electronics part, what we would usually do is that we would do the testing, right? Most likely it would be physical, and physical testing is something that eventually we will have to do. It's not something that we will completely ignore. So this is where HALT is done, right? I think the previous session was really insightful. I was also very, have a big fan there. Thank you for your time. So HALT, right, is done so that we want to force the components or the electronics parts to fail. Right, so we want to know where the weaknesses are. So after that is done, once that's done, we want to determine what is the root cause, right? Because designing something is not just, printing a lot of prototypes, and it's not just, having a lot of designs and then testing and see and hoping that one of them will succeed, will pass, right? We want to be able to design with intention, right? Because designing or physical prototypes can be a little bit expensive at times. I mean, it's crucial, but it might be a little bit expensive, right? It's not just the cost of the materials itself, it's also the testing, because it's not just, putting something and then just testing it and hoping it will pass. And also the cost of the people that have to do the testing itself as well. And it also takes time, right? I mean, if we have to do, I don't know, 100 tests on one prototype, then that's going to take a lot of time. And not only that, the process after that, the manufacturing or the time to market is going to, be extended. So that's the other things, and that's the risk that comes with physical prototyping. And the last risk is, what if it still fails, right? What if we can't correct it at the right point? What if we keep correcting, keep designing, but the same place still fails, right? How many more iterations do we need to do? How much longer do we need to keep testing? I'm sure as design engineers, we get this question a lot, right? When is it going to be done? So I think that's one thing that that is the risk that we all face, right? So virtual prototyping or using engineering simulation is becoming more, I would say, popular. It's being used more and more. Even though it says that it paves the road to zero prototype, personally, I believe that physical prototyping is not going away, but it can be used in conjunction with each other. So, and also electronics reliability, right? There's a lot of challenge with it. One challenge is the complexity in terms of the geometry, right? It has a lot of components, it has a lot of traces, it's a lot of layers, a lot of small parts that all of these combined, and all of this presents a lot of challenge to design engineers, right? Material complexity. I think that definitely is there because we have a lot of material types within the electronics, right? Just speaking of PCB itself, just the board itself has, I don't know how many layers of different materials, and with that presents complexity when it's what's the word? Sorry. When it's subjected to temperature. And finally, physics of itself, right? I think I'll talk a little bit more here. So with all the tests that we talked about, right, I think it makes us, if we were to summarize that, I think we can summarize it into the real world system, which is that electronics part are complex in the terms of physics because it involves multiple physics in itself. What do I mean by physics here? So first, when we design, right, we think about the signal integrity, the power, and all the electromagnetics part that comes with the design of the PCB itself. But with that will come the heat, right? With electronics, heat is definitely going to come. And with that, there's going to be a lot of temperature-dependent electromagnetic properties. A lot of complexities is going to come there. And then with thermal comes structural, right? I think that's why we're doing this HALT, right? Because when we subject the board or the electronics part to temperature, it expands or it shrinks, right? So that is going to be another complexity as well that we have to face. And then with all this in mind, we do design iterations, right? So again, it's very detailed, very complex. So engineering simulation can help you here. I will talk about why. So in the stage of product development cycle, we will still definitely keep the physical prototyping and the testing, but what we can do is kind of virtual HALT, I would say. I coined this term. So we create simulation models based on the testing models itself. But after it's failed, we can try to find where's the root cause. Why is it failing? How do we make it better? Right, so uncover all the weaknesses and also how the correct actions to take to make sure it passes the qualification. So let's talk a little bit about the applicable stresses in HALT and how engineering simulation fits in there. So first thing first is the usual, the typical HALT stresses that the PCB or the electronics parts will face. First, I'll talk about the thermal part of it. So thermal step, right? So you will both have to increase the temperature and also decrease the temperature, right? So you find the destructive limit of your part. Why? Because temperature is the leading cause of failure, right, for electronics, right? And we also know that if it's too hot, it expands. If there's a temperature drop, then it shrinks. And then with the different materials, right, it shrinks at different rate. So there is the weakness that is going to come out. So let's see what engineering simulation can do. So with warped, so we can actually simulate and see warped PCBs. So warped PCB will lead to all those different things. So the joint failures, delamination, cracking, component damage, and even fitting issues. So here we can identify thermal hotspots, stress concentrations, and look at the magnitude of the deformation as well. Delamination potential, right? And also finally the lifetime. Okay. So let's take a look here quickly. So on the lower side of the screen, you'll see, this contour of colors. So these are actually the deformation of the PCB and also with the components on it. So with PCBs or in electronics, right, you have a lot of fixtures. You have a lot of places where you would fix it to the electronics part. So that would also influence the shape itself, the shape of the deformation itself, and the location of the deformation. In addition to this, you can also see that as you increase the temperature or as you decrease the temperature, where the strains are. And you can also see if there are different layers of the PCB, you can also see the delamination potential. So you can look at the stress that is happening in each layer. So that is where you can also apply engineering simulation, right? So from my understanding, when you do HALT testing, most likely you are not going to consider the flow itself, or because it's inside a chamber, right? And then you just heat up the chamber. But in actual use cases, right, you will most likely attach some kind of cooling to it, right? When you design electronics, you will definitely not want it to heat up. So when you attach those, either it's a fan or some kind of cooling system, it's a heat sink or whatnot. So there's this thing called forced convection. So basically, convection is something that you would need to consider more and more. And also, the behavior of the flow, how and where the flow passes through is going to be more important in that case. So engineering simulation will also let you see at that point as well how the flow acts in the system that you have designed. Right. So the next one, I'll talk about thermal cycling. Right. So that's also something that I think in a lot of industries, not just electronics, but even like automotive parts, you have to design it to withstand a lot of thermal cycling. So thermal cycling, why are we really interested in it? It's because there's this thing called thermomechanical fatigue, right? So the temperature difference will cause all this strain from the differential expansion, right? Because the coefficient of thermal expansion is different on each material. And also, not only that, but the constraint on the board that I just mentioned will also affect the bending shape or the bending magnitude of the board and the strain that is going to be applied on all the components. And then finally, that strain is not going to just be on the board, on the components, but on the joints, on the solder joints as well. So with the simulation or with like the testing, the objective would be the accurate prediction, right, of failure location. So not only will it fail, but where it fails, and definitely number of cycles, right? When would it fail? Because with the market or the consumers these days, we want something that is better in every way, right? It has to be more reliable. It has to work in all of this environment, and it also has to work well. So when it fails, it's also going to be a good question to ask. So thermal cycling, one example. this QFN package placement. So where you place packages is also important, right? So if you place it in some place where it already has high strain, what happens is that this high strain area could lead to the solder joint failure. It could crack or it could actually fail. So you can see or you can look at this result before you actually try to place it and print out or produce the parts. Solder strain is another thing that that the previous speaker was talking about, right? So I think maybe, I don't know how many, maybe 10 years ago, there was a case of airplane crash where the investigation concluded that the airplane crashed because of solder joint crack, right? So that's one of the, I would say, main reasons for failure, or a very common reason for failure. So it's not only just the mismatch and all that, and it's just not knowing that at this temperature it will fail, or at this kind of cycling it will fail, but where exactly would it fail? So if you look at the image on the lower side of the screen, I think you will see that you'll see some red area. So that's where you can expect that the strain will be high and that it would fail first. So that's where you can use engineering simulation to predict all the solder joints. Okay. The last applicable stress that I would talk about in HALT is the vibration. So vibration is, if you look at that chart, that's the second leading cause of failure in electronics, right? But vibration has a lot of different kinds, right? Harmonic vibration, where there's one single frequency you test on. Modal analysis, where you test where you try to find the natural frequency of the electronics itself. And it's not just the board or the components, but the entire assembly, the entire package is something that you have to consider. And finally, random vibration. Because we don't know where our electronics is going to be used, and especially in automotive industry, random vibration is very common because we don't know where the car or the vehicle is going, right? We have no idea how they're going to use it. Sometimes, you know, the cars tested, stay in the roads of Bangkok, but then it's used in somewhere where it's very harsh condition and it fails, right? And then it becomes design problem. So random vibration is also something we have to take care of. So let's look at model analysis example. So model analysis, basically what you do and what you try to look at is you try to look at also the deformation shape, but also the mode, right? You need to find the mode where the electronics is going to have its natural frequency so that you don't use it in that mode. Because if you use it in the natural frequency mode, what happens is the deformation is going to be amplified and then it's going to fail even easier. So that's one example. Another example, this would be harmonic vibration, if I'm not mistaken. So this is vibration analysis of an entire PCB with all the traces, with all the components. In this case, you can see the red area at the lower side of the screen. So that's where the strain is highest. So what software can tell you, or engineering simulation can tell you, is that you can actually see, if you can see the 3 rows on top of the image, that is where you have the highest probability of failure of the component itself. So you can see that, okay, strain is high, but I'm not sure if that's going to fail. But the software can actually tell you what is the probability of failure in this case. So why would this be useful, right? So you can actually fix or you can actually redesign with the correct actions or in the right places. So you don't have to just randomly try to fix it, but you know where it's wrong or you know what's going on, and then you can try to fix it well. The other one is random vibration. This case, I think the images might be a bit confusing, but this is comparing random vibration with the natural frequency. So simulation can tell you what happens during the random vibration and also where the deformation or the strain is going to be highest. And in this case, it also tells you that, okay, the first mode shape of the natural frequency is actually the most dominant in the random vibration. So try to avoid that frequency. So that's what they're trying to establish here. Another thing is trying to compare between the experiment and engineering simulation. Image is a little bit small, but on the lower right-hand side of the screen, I hope you can see the crack circled in red. So you can see, you can compare the crack that actually happens in the experiment with the crack in the simulation that you can actually see. So this is trying to compare the results of both engineering simulation and experiment. Okay. Additionally, this is not traditionally in HALT, but dropped and impact is also quite important, right? I think one easy example is, let's say, your phone, right? I mean, if you drop your phone and then it immediately breaks and it never works again, then definitely, people are not going to come back to buy your phones or your electronics. So drop TED is also one thing that we can do, and not just for PCBs or just certain assemblies, but you can fit anything in there. So if you have the housing, if you have even larger system, you can also try to do drop test on that as well. So drop is more common, I would say, but impact, as in crash, that's also possible because that uses the same physics. Yeah. Okay. Sorry. If there is one software or one tool that I would like to introduce that I would say is the most appropriate for reliability of electronics, it would be this one. So, the industry challenges, because you are all in the industry, the high standards, the predictive analysis, the designing for reliability, right? So all this. What I would like to introduce is is a tool called ANSYS Sherlock. So why is ANSYS Sherlock the one that I talk about? It's because it's the physics-based design analysis software specifically made for electronics. So Sherlock, one thing that it does, I think which is going to be very helpful, is you can translate your HCAD files. You can just input that into Sherlock, and then it will translate that into an CAE or FEA model. So you don't need to manually translate. And it can also do accurate predictions of a lot of different failure types. So thermal cycling, mechanical shock, natural frequency, harmonic, and random vibration. So most or all of the HALT tests, stresses that you would have to do, you can also do it in ANSYS Sherlock. So some key features that I would like to mention. I think this would be found very helpful. Sherlock has extensive library of parts, packages, materials, laminates, soldiers, it's all there. You can pick and choose and use all those. It also does, failure, as mentioned. So not just one kind of failure. Thermal cycling, I will show you one example of thermal cycling use case from now on. But okay, again, mechanical shock, natural frequencies, all that. And it also does reliability prediction. So it tells you after so-and-so cycles, what's the probability of this electronics part failing. And not just, and not just for all the tests, but for individual tests as well. You can also, it will calculate the lifetime, when it would fail, and what's the possibility of that actually failing. Okay, let's look at one case study. This case study is based on the objective that they want to identify the solder geometry that would yield the lowest probability of failure for the electronics part. Okay. So there are three kinds of geometries of solder that they would do. They subject this to 1,000 temperature cycles in the simulation. So I hope you can see the right-hand side of the screen. That's the temperature cycle that you can input. And then the software will let you know what is the probability of this electronics failing. So counting from left to right, that's the design 1, 2, 3. So it's a little bit small, but you can see that the third one, I think the bulkiest shape of solder is the one with the lowest probability of failure. I mean, it sounds intuitive, but yeah, you can test different geometries, test different configurations as well. Okay, so again, I think we've talked about this, but designing electronics isn't a straight line, right? It's not just electronics and then that's it. It's multi-physics, electrical, thermal, and structural. So, so going beyond ANSYS Sherlock, we can also look at different kinds of physics as well, or more in-depth physics of each phenomena as well. For example, so as I mentioned before, electronics will produce heat, right? So with all the loss and power dissipation, you will be able to simulate or see the thermal distribution, the temperature distribution in your electronics. And with that, you can also add your flow. So if you wanted to add a fan or some kind of flow device in there, that's also possible. And then with that, you can also see, in this case, in this specific case with all the fans and everything, what would be the deformation or what would be the stresses that happens to the electronics that you have designed. Okay. So quick summary for ANSYS Sherlock. So ANSYS Sherlock is failure-based reality analysis. So it's built specifically for electronics. So it has all these workflows that you can follow, and all the interface is kind of adjusted to be used for electronics. And finally, you can also couple it with more advanced physics like drop or thermal with convection, with forced convection. That's also possible as well. So a little bit about us, about CADFEM, and also about all the simulation that I was talking about. So I'm from CADFEM, so we are the largest ANSYS Elite Channel partner. So we have started doing engineering simulation for 40 years, and with that we have 30 plus locations in the world, and we also have 5, maybe right now it could be 6 3,000 clients globally. But I want to talk about ANSYS, actually, because I think we have seen that with engineering simulation, there's quite a lot of things that we can do. And how do we do that? Like, how is it possible that one solution has so many different physics inside? So ANSYS is the tool or software for that, because it's the #1 in simulation, and it also have a lot of different physics you can consider. So not just structurals or electronics, thermal, you could go down to optics, photonics, that's also possible. So all these things can be considered with the tool here. My short key takeaways, I would say. We can use engineering simulation to perform virtual HALT. So even before any physical modifications has to be done. And also, you can predict the lifetime of your electronics product. So not only where it fails, but when it fails as well. And finally, you can also couple between different physics, which would be affecting your design. All right, thank you very much for your attention, and I hope the session was useful in some way. Yeah, thank you.